Hello there, welcome to a presentation on a kind of a tutorial to explain how we use the method of undetermined coefficients to solve. In this case, in this presentation in particular, we're looking at homogeneous linear equations of any order. In particular, here we're going to go up to order 2, and then we're hoping that that can be extended to order 3, 4, and so on. So in the previous presentation, ended up looking at the example which was d2y dx squared plus 3 dy dx plus 2y equals to 0, this homogeneous equation. So this is simply what is given. And now what you notice that the process of solving this equation, this is solution here, starts. First of all, we said it will start by extracting the characteristic equation, which we're going to do this way. In the back of our mind, we're not going to go through the whole process of analysis we did in that example. If you didn't understand it, you must go back to the presentation and see what we did. We said here, in the back of our mind, we must have that d0 dx, the 0. This is the identity operator, differential operator, which you can look at as 1, and when you apply it to a function y, we simply get y. And then d, first order differential operator, that we're going to set it as a parameter m, and then in this particular case d2 dx, we're going to set that as a parameter m squared. Now if we look at that in that fashion, so if we come here, we're simply going to have m squared for the differential operator 2 multiplied by y plus 3m plus 2, sorry, 3my plus 2y equals to 0. Again, this step is a step which we can omit. If we've mastered this, we can simply, from there, we can simply get to m squared plus 3m plus 2 equals to 0. Because remember, this should take us to writing m squared plus 3m plus 2 in brackets, just extracting common factor the y equals to 0, then coming and saying therefore m squared plus 3m plus 2 is equal to 0, and here y is considered to be a non-trivial solution. So we can straight out from that given equation come here. Then the next thing we said, then it will be factorizing this. We saw that we just factorized it as m plus 2 multiplied by m plus 1, and then equals to 0, and finally this gives us m equals to minus 2 or m equals to minus 1. So our task today is to just learn exactly what do we do with this to determine the solution to the differential equation given. So we're going to start with this example. Like, then let's say we're given the problem here, we're given d2y dx squared plus 3 dy dx plus 2y equals to 0. Now it's here setting the right hand side equals to 0 to get to a homogeneous equation. We've already seen this. Then Our initial step is, I'll write here CH EQN for characteristic equation. Now extracting that, this will be simple m squared for that operator plus 3 times operator here, which is 3m plus 2 equals to 0. After extraction, solving this, we got m plus 2 m plus by m plus 1 as factors of this left hand side equals to 0, and therefore landing at m equals to minus 2 or m equals to minus 1. Now the question is, what do we do with these two? There are two solutions because our characteristic equation is an equation of order 2. Then now we simply come here and say 2. Now we're building our solution. Building our solution, we're going to do it as follows. We're simply going to say here y, in this case going to be our general solution, yg, it will be equals to, we take these roots of the characteristic equation and use them as follows. We're going to say first of all c, like we saw in the first example we looked at. In this case we're going to say c1 here, or we can use a and b, or a, b, c, d. Remember, I prefer to use c1 here, the first constant. It will be c1 times e to the power minus 2x plus c2 to use with the second constant, e to the power minus x, our coefficient there of x being minus 1. Then we've got a solution. Then it's normal people for to be suspicious, saying, is this really a solution? Let's then test that this is a solution, so that as we go forward, we now know that we've got a reliable method of finding a solution. What did you do? Testing whether this is a solution. Here is an equation. So what we're going to do, first of all, we're going to say this is our y. The next will be our y prime for this, which will give us here minus 2c1 e to the power minus 2x minus c2 e to the power minus x. That's the derivative, the first derivative which we need here. We can denote this as dy dx. Now this is dy, our general solution, dy dx. The next thing now will be to find the y second, which is simply our d2 y dx2. And then now we're differentiating this. So what we're going to do here, we're going to say, if they differentiate this again, we're going to get a minus 2 again, then get 4c1 e to the power minus 2x plus c2 e to the power minus x. That will be our second derivative. Now substituting in this, we're going to substitute as follows. Let me just try to squeeze this solution here. First thing here, we've got 2 times y, which is 2 times this. We write here 2c1 e to the power minus 2x, sorry, plus 2c2 e to the power minus x. Let me just create a division here. And then the next thing is 3 times the first derivative, so which means multiply this one by the first derivative, which is going to give us minus 6c1 e to the power minus 2x minus 3 e minus 3c2 e to the power minus x plus the second derivative, which is this one, which is simply 4c1 e to the power minus 2x plus c1 e to the power minus x, and this we are all adding, and this will give us what? The left hand side, and we know that we see here that the right hand side is equal to 0, so we've got to see whether this gives us 0. Let's simplify this. What we have here, we've got 2c1 plus 2c1, which gives us 6c1 e to the power minus 2x, plus minus 6, we get a 0 here, plus this side we've got here 1c1 plus 2c1, which gives us 3c1 minus 3, sorry, this is c2, sorry, c2 is 1c2 plus 2c2 times e to the power minus x plus minus 3c2, which gives us 0. So we get this equals to 0, which is equal to the right hand side. We can now conclude that therefore this is a solution to the given homogeneous equation. So this is our first example. So what you notice here, with the characteristic equation, which gives us two real roots. Here we've got two real roots, and in this presentation what we see that these two real roots actually gives us two terms of the equation in this way. Each term, this being sort of the variable scaling of the exponential function here. So the variable for the exponential function y is equal to ex. Instead of being simple 1, is the variable there is scaled by minus 2, which is the solution there, and in this case by minus 1. So the most important here is to master how you take the solution of the equation, the two of them, and they build up a solution, in this case involving two undetermined coefficients. So two solutions, two undetermined coefficients, then adding the two terms, and each one of these terms individually is a solution, which takes us to the fact that we must know that if we've got two solutions of a differential equation, two different solutions of a differential equation, their sum is also a solution to the differential equation. You can test that alone, that take y is equal to c1 e to the power minus 2x, and verify exactly the same way with the solution, and also take y equals to c2 e to the power minus x. You see that individually these are solution, and their sum also here is a solution. So I hope you have seen what we do when you've got two different roots like we have here. So let's proceed and get to the next example. This example, okay, this is fine. Now our next example is as follows. We're given this differential equation, we're given d2y dx 2 plus 2 dy dx plus y equals to 0. So now we're going to be a little bit faster. Characteristic equation will be simple: m squared plus 2m plus 1 equals to 0. Next step, solving this gives us m plus 1, m plus 1 equals 2, which in this case here you've got m plus 1 squared equals to 0. In this case here, this is the case where we say this is a perfect square, a factor is repeated, and the roots we get here, we're going to call them repeated roots. Repeated roots. What do you mean? If what I mean here, basically we're going to say m plus 1 is equals to 0. But because the two factors there of the same nature, then I will say here twice. Meaning the factor is repeated, so the root is repeated. So then what we're going to have here, we're going to say m is equal to minus 1, actually twice, to maintain that. Then number 2, now observe that in this case now we've arrived at real roots. M as a root here is still a real number. In this case it is repeated, it occurs twice. What we're going to do here, you should try to see what are we going to do if it was repeated thrice, 4 times, and so on. But now you're just going to deal with twice here. So what we have here, well, now writing the solution here, we're going to do this as follows. This is our general solution here. We're basically going to say the solution is C1 e to the power minus x. In this case here, this is the first term. Now it's e to the power minus x. This root is used for the first term, plus C2 t e to the power minus x plus C2 x e to the power minus x. Now it is used for the second time. Now note, when it's used now, the root is used for the second time. Note what I've done here. I've included here x. Then let me interpret this thing for you again. What I've actually written here is C1. The root is used for the first time. Then I write here x to the power 0 times e to the power minus x, that is used for the first time. So this is our initial use. We've got our x written there as power 0, plus C2. Now we're using this for the second time. Now from initial that we make one step, we write here x to the power 1. From our initial term, make one step, x to the power 1, e to the power minus x. That's how what is done there. So whereas we are seeing this way, we must understand that here, when the root is used for the first time, the variable x is to the power 0. When it's used for the second time, one step, that variable x is to the power 1. So simplifying this will look like C1, x to the power 0 is 1, C1 plus C2 times x multiplied by e to the power minus x. That will be our solution. This is the form of the solution when the roots are repeated. In this case, repeated twice. Now we can simply, maybe looking at this, we can simply try to figure out what would happen if this m was repeated twice. Let's say if m was equal to minus 1 3 times, for example, 3 times. Let's say it was repeated 3 times. We'll do exactly the same thing. Our y in that case will be y general it will be C1, or can even start from C0 to be sort of make it easy to remember. So C0, and then say this is the first time this is used, then we say x to the power 0, e to the power minus x, plus C1, x to the power 1, e to the power minus x. Now here we've used it twice. Then it's repeated thrice. You're going to go to using it the third time. Then you come here, say C2 x to the power 2, e to the power minus x, and then simplifying this we are going to have here C0 plus C1 x plus C2 x squared, which is simply a polynomial of order 2, in this case 1 less than the number of repetition, and here it was a polynomial linear order 1 repetition 2, 1 less than that. So we have got this way, then e to the power minus x. This is what we do when it is repeated twice. So I hope now you can extend this to when it's repeated 4 times, 5 times, 6 times, and so on. That's what we do. So here we've got repeated real roots. This is how we handle it. I hope that is clear. So what you can do now is to get your text and try to practice this similar example. But before we get there, let's look at the last example for this presentation. Here is the equation. We're given d2y dx 2 minus 2 dy dx plus 2y equals to 0. So initial step now, quicker, you just get to the straight to the characteristic equation. 2m to the power 2 minus 2m plus 2 equals to 0. Next step, we try to look at this and see whether we can factorize, but this cannot be factorized. Now, since there are no factors, what we do equivalently, if you cannot factorize, we move on and try to use the quadratic formula or completion of square, whichever way you want to look at it. So let's look at here now as m1 and m2. I'm just indicating that we're going to get two solutions here. Then applying a quadratic formula. I'm first going to remind you the quadratic formula. It was, if we've got this as x squared and that it would be minus b here plus or minus the square root of b squared minus 4ac all over 2a. So in our case here, our x is m, our a is equal to 1, our b is equal to minus 2, our c is equal to 2. Substituting here, we're going to get 2 plus or minus the square root of b squared, which is 4, minus 4ac, which is minus 4 times 2 times 1. 2 for c, 1 for a, all over 2 times 1, which is 2. And this lends us at 2 plus or minus, and this is 8 minus 8 plus 4, which is going to give us minus 4 all over 2. And you can see clear that this lends us at what? At complex roots. And then we've got here as, going to write this as 2 plus or minus I squared for minus 1 in here, 2 squared for 4, under the square root all over 2. And this gives us 2 plus minus 2i, the imaginary unit, all over 2. And then this gives us 1 plus I. Let's write this as a general complex number, which we can write as alpha plus I beta plus or minus I beta. But in this case here, in general, we can just look at the root as z equals to alpha plus I beta. To mean that if I've got a number z alpha plus I beta, we must always know that the conjugate, in other words with the minus here, is also a root. But for the purpose of writing our solution here, we're simply going to look at this number as it is here, as if we got the solution as alpha plus I beta. Noting that now alpha is the real part of z, and the beta is the imaginary part of our complex root z. So now we've got simply to use these two to write our solution. This is how we're going to do it. We're going to say now our general solution yg is equals to e to the power alpha x, x the independent variable for that, in brackets a cosine beta x plus b sine beta x. That will be a general solution. I reiterate, look, observe what happens to the parts of this complex number here. Alpha comes here and becomes a scaling variable, a scaling factor for this exponential function there. And beta comes here and be the angular velocity for the two sinusoidal waves here, cosine and the sine. That's very important. So if you look at what we've done now up to this point, we looked first at different roots, real roots. We saw how we build the solution, and then we looked at repeated roots. We saw how we build the solution, and the third, now we see that what happens if we've got the complex roots. We solve the equation, which in most cases we can solve using the quadratic formula or completion square and get the complex roots. Then we look at the complex roots given as just simply alpha plus I beta, and then use the parts, the real part and the imaginary part, to make up the solution this way. What I leave to you is some kind of homework. You can now take this equation, this expression, and see, verify whether it really satisfies this equation. Okay, having seen this now, I think the next thing is practice of this homogeneous case. So of course with the different types of roots, now it's different real roots, repeated real roots, and the complex roots. I'll then post to you a compilation of few exercises as your initial practice on this kind of work. Otherwise, at this point, I would like to say thank you for listening. My name is Charles Wasfanamsi.